All right, recording is rolling. It's Thursday, October 5th. Here's top scientist for dynamics quiz. Actually, I'm gonna probably just use this video for all my classes since they're pretty similar. So here's the honors version. So awesome job if you're on this list for dynamics. All right, so yesterday was a little bit off day. How'd you guys do that circles measuring activity? But we're gonna continue from. We were actually doing a lab setup a couple days back for this centripetal force lab. Okay? So that's what we're doing today. Remind you guys how this is working. Take you guys through some thoughts here. Okay? So here, you guys may get PVC pipe, string, a couple Play-Doh canisters, maybe some masses that you can load in here. Okay? And then I'll wheel this around in a horizontal circle, right? And then, okay, so this Play-Doh canister is pulling down. This is providing a weight, right? Which is keep everything in check, right? And this green canister is like flying around a circle. On video screen here, do a quick demo. Right? So you guys see that? Right? See how that radial size? I'm trying to keep a pretty consistent size, right? Because if I spin it faster, the radial size opens up. If I spin it slower, then it'll get smaller. Right? But there might be like some sizing stuff, right? So what's the balance of variables here? I see four variables that we're juggling. Right? There's some weight that's hanging, right, providing this force. Right? Now, if this is in true static equilibrium, that means that the tension up is balancing weight down. Right? So the tension is transferred through the string, and the tension, that's the force that's pulling this mass into a circle, isn't it? Right? Anything on a curved path, there must be an external force. Right? What we haven't quite addressed, up until this week, is what force is involved with like changing direction, because you guys know forces cause accelerations, right? But up until last week, we were just focused on like speeding up, slowing down in a straight line. Right now, we're saying, well, what force can actually cause you to like change your direction? Right? It's called a centripetal force, right? And in this case, it's the tension of the string, which is equivalent to this weight down here. So I'll just call it F for force, right? We've also got what's the mass of the one that's in the horizontal circle, right? What's the radial size of that circular path, right? And how fast is it going speed? So v comes from like velocity, but I want to be careful about using the term velocity because velocity is changing because the direction is changing. Now, the speed can be constant. Right? So I would call that tangential velocity, right? Like if you cut the string, it wants to go off the straight line path, right? So we have these four variables that we're juggling. So, well-crafted experiment, you just want one independent variable at a time and then try to control everything else, one dependent, right? So you guys have one of four suits on your desk. Okay. If you have the spades, I'm gonna have well here, big picture. I'm having everybody relate everything to the speed right here, right? So everybody's gonna treat speed sort of as a dependent variable, right? You're gonna have one of these other three as independent and the other two as controls, right? So if you have the spades, you're gonna treat the top mass as your independent variable, right? And speed as dependent, right? If you do that, you're leaving the bottom canister, that weight, you're leaving constant, right? And also this radial size. Now, guys, this is one of those labs that if you're really meticulous about collecting your data, so suppose you have like a 40 centimeter radius, make sure it's always 40 centimeters all the way down, like controlled variable. Okay? If you're really careful about that and you do it right, then all the data at the end, when we plot it all on axes, make graphs, is going to look really nice. It's going to lead exactly straight to the textbook solution. I've seen that outcome. On the other hand, if you're not really tracking this radius very well, and sometimes you have small radius, sometimes big radius, and you're like really sloppy about that, the data is also going to be really sloppy, and the graph's going to be all over the place and not really make any sense. Okay, so yeah, so if you're controlling the radius, definitely make sure that you're using the same radius like all day today. Okay? If you have the diamonds, then you'll leave the top canister closed, but the bottom canister, maybe you can make heavier, heavier, heavier. Ooh, if you make this one heavier, you think I have to probably swing this around faster? Maybe something like that to maintain some, again, like some consistent radial size. Right? Radial size is controlled for each of those two. Right? Is it? Right. If you have the clubs, you'll leave the two canisters sealed all class period, but you'll treat the radius as an independent variable. Right? So you might go like 20 centimeters, 30 centimeters, 40, 50, 60, 70, something like that. Right? Maybe slip in 10 centimeters if you can. Right? Something like that. Right? And then again, control these two canisters. I should mention these canisters. You guys know you're going to have these mass slugs. You can pop in the canisters. Okay, right? But the canister itself, this plastic, has some mass. Okay? So I put on the board some estimates. If you get a little tiny these little tiny canisters, they're about 6 grams each. The big canisters are about 12 grams each. That's not exact, that's ballpark. There's a digital scale back there. So if you want to get like a more accurate number, you can put these on the scale. Right? But if you just want to add, okay, I've got like 10 grams here, I can pop that inside 6 grams, and that makes 16 grams. Right? That'll be close enough. It'll these graphs will look pretty good from that. If you have the pink card on your desk, we'll treat that as, well, I've been treating that as wild cards, so just choose one of the above. But in this class, it looks like we'll otherwise be short on diamonds. So tell you what, if you got the hearts, go ahead and pretend that you have diamonds, and I think that will give us plenty of data. Okay, guys see that? All right, let's look at this table that you guys had started back a couple days back. Right? Okay. So we've got 11 columns here. Do you guys write your name on your paper? Did you guys write Centripetal Force Lab? Right, so Centripetal Force Lab, you guys got your name, right? Right, so we've got trial, 1, 2, 3, 4, 5, 6, 7. Try to get at least 5 different data points, right? Right, so what's the mass that's hanging, say like in grams, right? Typically use kilograms, but let's just, grams today, it's got small masses. Right? Now, I don't really care about the mass that's hanging, but I do care about the weight, right? How do you go from mass to weight? Just multiply by a gravity field, 10 meters per second squared, right? But if we're in grams instead of kilograms, suppose it's like 16 grams. Yeah, 16 grams times 10, that's 160, but that's not newtons, that's millinewtons, right? So 16 grams weighs 160 millinewtons, right? Because we're down by a factor of 1,000, right? What's the mass that's swinging 80 grams, right? We really care about what's the proportional relationship among these variables. So once you pick some unit to measure, let's get it, okay? Right. What's the reciprocal of that mass? If I ever just say mass out of context for this lab, I'm almost certainly talking about the swinging mass, right? Because that's really the mass that I care about. I care about this mass that's swinging around, right? The one that's hanging, I really care about its weight, like as a force. What's the radial size of the circle, right? Say like in centimeters. You can do meters, it's fine, meters or centimeters, right? Right, and then like take the reciprocal of that, right? I think that's about where the bell rang last time I saw you guys. Now I starred the 3 potential independent variables. So depending on which suit is on your desk, one of these is an independent variable and the other 2 are controls, right? Wouldn't that be true? Right? And this whole thing about like finding reciprocals and stuff that may or may not be applicable to what you're doing, but I'll show you guys some access setup later too. Right? These last columns have something to do with the speed or getting the speed one or another, right? Well, how are you going to get speed? Hey guys, is speed distance divided by time, right? And guys, what is the distance around the circle? Circumference, right? Oh, and you guys know circumference. Yesterday, your guys' circle measurement lab, yes, its circumference is 2 pi r, right? Okay, so if you know what the radius is, because that's already one of your measured values, right? You can kind of hold the meter stick up to your circle, right? See, okay, got 40 centimeters radius. Right? Can you guys just go 2 pi r and get the distance around? Right? Maybe I should have made that a column, but just gonna do that, right? But how much time will it take? Because distance divided by time, right? So you guys have some stopwatches back there. You could time 1 revolution. The tricky thing about that is, you guys know stopwatch, it's really tricky to get start and stop exactly correct. Right? But what if you do 10 revolutions and then divide by 10? So suppose it's like comes out to like 11 seconds, and then divide that by 10. It'd be 1.1 seconds per revolution, right? The advantage of doing that is whatever error is involved with starting and stopping, suppose you're off by like 1 second, that also gets divided by 10. So now you have a lot more accurate time for time period, right? Right. So then once you got, okay, so the time for 10 revolutions, so it's like 11 seconds. The time for 1 revolution, it's just that divided by 10, it's like 1.1 seconds, for example. What is the speed? Right? Well, that's just 2 pi r divided by the time period, right? Circumference divided by time period, distance over time, right? You guys got that? Now, this very last column, just go ahead and square that value, whatever it is, right? And everybody will need this last column, regardless of which suit is on your desk. It's going to be useful to square the speeds. Okay. Now, why? You guys will see probably before the weekend. Right? It's kind of related concept to some stuff we did yesterday. This is yesterday's lab, right? You guys remember circumference is 2 pi r. Hey, that's a connection to today too, right? But there was this linearization idea. The idea of like if you have parabolas, you can figure out an equation by just linearizing by manipulating an axis. Right? That's gonna be showing up here pretty soon too. All right, you guys good so far? You guys got the table? Okay. Okay. Very good. Try that. All right. So, if you get enough data today, you might be able to start with these graphs, and then tomorrow we'll put all these 7 graphs together. Right? But depending on which suit you have, you'll be able to do either 2 or 3 of these graphs, but 7 all together. Okay, right? And then we'll be able to take these relationships and actually put together some master formula that's going to tell you the relationship among these four variables, right? What is the force that is effectively the centripetal force, right? How is that related to this swinging mass on this curved path of radius r moving at some speed v, right? There's some connection there, right? So some formula you can fit it on into, right? Right. You guys go there? Right. One last thing for you guys. Okay, since you guys are AP, I'm gonna have you guys do a 5-part write-up for this. Okay. So question here. Here's a question right here. What is the relationship between blah and blah variable, right? Depending on which card is on your desk, right? For the mass on a string of circular motion. Boom. That's the question, right? What's the relationship between these two variables, right? With the other two controlled, right? Of course, there's 3 different perspectives on that. We're gonna take those 3 perspectives to make one giant equation for that. Right? What's your measuring tools? Oh, guys, what are the measuring tools today? What, and what? Yeah, there you go. That's it. Scale, meter stick, stopwatch. Boom, boom, boom. Right, that's it. Right, so boom, boom, got those 2. Data gathering procedure. Here, I'll help you guys out. I whipped up this procedure in like 2 minutes earlier today. Procedure. So first step is like just very briefly explain the setup. Connect 2 canisters on a string through a pipe. Swing 1 canister in a horizontal circle, letting the other canister act as weight. Boom. That's the entire setup right there. Right. Your next steps are like measure what variable with what measuring tool. Measure the mass of each canister with a scale. Boom. Point. Measure the radius of the circle with the meter stick. Boom. Point. Measure the time for 10 revolutions, divide by 10 to get 1 time period. Boom. Point. Right. There's 3 measurements. Right. Speed. 2 pi r divided by t. Boom. Point. Right. We need to somehow explain an independent variable. So change whatever independent variable, whatever experiment you're doing. Right. Leave the other 2 constant because those would be controls. Boom. Point. Right. There's always AP is always looking for like multiple trials. Right. So do multiple trials and then take an average to reduce experimental uncertainty. Right. They're always looking for that point. That's always a point. Okay. Right. So that's procedure. Okay. Analysis is going to be the graphs. So your analysis is going to be, well, one of these rows, depending on which suit you have. Right. And then conclusion is you can say what variables directly proportional to what variable, or maybe it's something like b squared is proportional to something, right? Okay. And then we'll take those 3 different proportionalities from 3 different groups, and we'll put them together to make one giant equation. Right. If they do individually, we'll know 1 proportion. Okay. Right. You guys get that? Right. One last thing before you guys head back there. There's always like a bunch of little tips I can give you. Here, well, I'll give you guys a couple of tips. How about that? Or I'll ask you guys, which makes more sense? Which is going to make more sense? Which canister should be heavier, the hanging one or the swinging one? Yeah, the hanging one. Yeah, you want the hanging one to be heavy and the swinging one to be kind of light. Right. You guys will see when you get your hands on these. Here's another thing. If you guys start popping off these Play-Doh lids and then like putting in masses and then closing the lids back, what's a good way to attach a string? Should you just like put a piece of tape right there on the string and hope that holds on? No, that's gonna fall off. Right? Should you just like put the string in there and then pop it like that? That's probably not good too. That's gonna probably slip off. Right? Watch this trick. Watch this trick. Okay. What if I do something like this? Okay. Do you guys see 1, 2, 3, 4 locations where the string crosses the edge? Okay. Okay. So 1, 2, 3, 4 location. Then pop that on. Okay. Like no way is that gonna come off. And then there's also some rolls of tape back there. So if you throw on some tape, yeah, that would be like super secure. All right, guys got that? All right, so everything you need is back there. See if you can gather at least 5 data points, maybe make some graphs by the end of class and have a procedure. And then tomorrow we'll put everything together and I'll also break out some grading rubrics for your AP procedures. All right.